come to that discussion a little bit later in the second half of the lecture. First half, I want to discuss further about the applications of work by energy, and particularly I want to discuss about the applications of constraint relations in work by energy. So this is session number 5. We were discussing last time about applications of work energy theorem, where we saw that for a system, the work done by external forces plus work done by non-conservative forces equals to the change in kinetic energy plus the change in mechanical energy. Okay, the change in kinetic energy plus change in potential energy. Now, in some textbooks, this might be written in slightly different way, that net work done by external forces plus non-conservative forces equals to the change in mechanical energy. So this is understood as the same thing as the above, where the left hand side is the same as work done by external plus non-conservative, and right hand side the mechanical energy of a system, or the total mechanical energy, sometimes we call it that also. It is the sum of kinetic energy plus potential energy. Okay. And then of course we saw certain situations where the left hand side of this is 0, so the mechanical energy is conserved. So those are the situations where we apply the conservation of mechanical energy, and so on and so forth. So now let's look at some examples of a bit advanced type of application of this concept. Okay, so let's start with an example like this today. We have this situation where on a smooth horizontal surface, we have one block which is kept like this, with a thread tied to it. The thread is going around a standard pulley attached like this to a ceiling. Now we also have the thread other side going around a second pulley, then finally attached to the ceiling like this, and another block like this. Okay, so these blocks are A and B. Now this surface has coefficient of friction equal to 0.2. Both the blocks have the same mass. Mass of A is equal to mass of B, equal to 5 kg, suppose. Okay, and this height is given to us as 24 meters, and this angle is theta. So now the question says that this system is released from rest. This system is released from rest with the threads, or with the thread taut, okay, at theta equal to 37 degrees initially. Okay. So find VA and VB, the speed of the two blocks, an instant when theta is equal to 53 degrees. Okay, so just take down the diagram and start working on it. I'll explain what all we have to do over here. So assume that by the time the thread's angle becomes 53, the block B hasn't hit the ground yet. So assuming B is not yet hit the ground, Just try out this question, people. Okay, so let's see how we'll make use of these particular aspects here to work this out. Okay, so you can understand that initially in this situation, what is happening is that our theta is 37 degrees and both the blocks are starting from rest. This is the picture at t equal to 0. Now, after some time, A has reached here, let's say. So by then it has released some thread. And as a result of that, it's released the pulley a little bit. Okay. So B has gone down and reached here. So this is at some time t, when this angle has become 53 degrees. So at that point of time, let's say A has a velocity dA like this, and B has a velocity BB like this. Okay. And of course, there is tension T acting in the thread like this. So in the original diagram, if this hypotenuse was L1, okay, and also this base length was X1. Now in the new diagram, this hypotenuse is L2 and this base length is X2. So we have to develop this couple of constraint relations. So if this has come down by Y, we can see that from thread length conservation, we have L1 minus L2 is equal to 2Y. Now L1 is going to be H by sine 37. So that is 5 by 3H. And L2 is going to be H by sine 53. So that is 5 by 4H. Okay, so that's the first thing. So we have 5H into 1 by 3 minus 1 by 4 is equal to 2Y. Then secondly, we have X1 is equal to H by tan 37. So that is 4h by 3. And x2 is h by tan 53. So that is 3h by 4. So this one's displacement is x1 minus x2. So that is this much. Okay. So this is our second constraint relation. Okay. Now you take A plus B plus the thread plus the, we also have the virtual power concept. So the block A is moving with the velocity VA like this. The tension at that instant is acting at an angle of 53 degrees, whereas the block B at that same instant is coming down with VB, and the tension acting on it is of magnitude 2T upwards. So TVA cos 53 minus 2TVB is equal to 0. So that is 3 by 5 VA is equal to 2 VB. That is VA is to VB will be 10 is to 3. So that is coming from a virtual power theorem. Okay. And now finally we come down to this as a system. So work done by friction on the block E should be equal to change in kinetic energy of A plus change in kinetic energy of B plus change in gravitational potential energy of B. This would be the statement of work energy theorem. So work done by friction will become, okay, let's do one thing. Here, let's remove friction. Let's make this a smooth surface because work done by friction will not be possible to calculate. Because so this is a smooth surface. So you don't need to calculate. So just make this correction here, people. This should be a smooth surface. So change in kinetic energy for A will be half mVA square. Change in kinetic energy for B will be half mVB square. And this will be minus mgy. Okay. So we don't this part also now because we are taking a smooth surface. So we just need the value of y, which we'll get from this. So y will come out to be 5 meters. Okay. Yes, Nikita, we are not considering friction because it will not be possible to calculate work done by friction because the normal reaction is varying continuously because of tension acting at a variable angle. So it will not be possible to calculate the work done by friction. That's why. Okay, so I'll tell you in what type of question like this we will consider friction. It will be a reverse type of question where, you know, one of the speeds will be given to us and we have to calculate the work done by friction or something like this. Okay, but in this type of question it will not be possible because, you know, there is no information to calculate work done by friction because tension is varying continuously. So anyway, so because of that, normal reaction is varying continuously. So anyway, let's get back to this. So we will get the relation that VA square plus VB square should be equal to 2GH, and then we'll use this relation. So we can say that VB is equal to how much now? VB is equal to 3 by 10 VA. So we can take, so 1 plus 9 by 100 is equal to H. Okay, so that's it. Now we'll substitute the value of H ke jagah, sorry, Y, no, my mistake, not H. This should be Y. So Y we already got as 5 meters. Okay, so we will substitute that numerically. So we'll substitute Y as 5 meters, G as 10 meters per second square, and we'll get the value for VA. And whatever we get will be in meters per second. And then VB is just going to be 3 by 10 that. So that also we'll get in meters per second. Okay. So this is just another question to explain to you the importance of the virtual power method for constraint relation. Okay, this is extremely important. So hope all of you have understood this. We have done a question like this about the initial acceleration earlier in Newton's laws of motion, and we saw that we can calculate the initial acceleration only at the instant when theta is, when VA and VB are 0, because you have this general relation that what happens in this case is that 2 VA cos theta is equal to, VA cos theta is equal to 2 VB. Okay, so when you differentiate this relation for acceleration, it's actually a very problematic equation. When you differentiate this, you will get acceleration of A into cos theta minus VA sin theta into d theta by dt should 2 times acceleration of B. This is the general constraint relation for acceleration. So for example, if you want to find this out now at this instant, VA you will get by work energy, like we have calculated. Okay, but that d theta by dt will also have to be calculated. So how we'll get d theta by dt? We will get it again by another constraint relation. You can see that as this block is moving, this is a fixed length and this is a variable length, let's say x. So you have x is equal to h cot theta, right? That is correct. So dx by dt will become minus h cosec square theta d theta by dt. Okay, and dx by dt will be nothing but minus of VA, because x is decreasing at the rate of VA. So minus VA is minus h cosec square theta d theta by dt. So we'll have to substitute d theta by dt as VA upon h sine square theta, cosec square theta will get, okay. And then we'll have to substitute that in this relation. So that will give a relation between acceleration of A and acceleration of B, that relation. Okay. So generally at JE level, you will not be asked something like this because it's too lengthy. You will only be asked up to solving the work energy theorem. But if I wanted the relation between acceleration of A and acceleration of B, I would actually have to do this. I have to solve for d theta by dt, the sine theta into d theta by dt, which you're getting by differentiating this. Okay. So this is a different matter. Okay. This is not concerning this question. This is for a constraint relation between acceleration of A and acceleration of B, which is something more complicated like that. Okay, anyhow, so we will do one more interesting question to do with this type of constraint relation in work energy, and then we will come back to some more basic things again. So we have quite a few things yet to cover in work energy. For example, we haven't even seen the application of power yet, the definition of power. We have seen in virtual power theorem, but in this chapter, so we have to discuss that also. Okay. Then we have to discuss more about the relationship between this thing, internal conservative force and potential energy. So few things we have to do. But anyway, let's get back to this. So this is actually more like a small particle rather than a block. So this is attached to another thread. Which is going around a pulley like this now. Holding another block. Okay. So A has a mass of 2m, B has a mass of m, and this total length is 2l, whereas this length is l. So basically this length is l and this length is l. A itself is small compared to this, so you neglect the size of A and B. They're small, very small objects, so you can treat them like particles. Okay, so initially you're holding the block B with the thread such that this part is horizontal. So initially B is held by an external agent such that the thread is taut and the upper part with A is horizontal. The upper part of the thread system is horizontal. So now B is released. Okay. So find VA and VB at the instant when A is just about to hit the wall. So this is attached, this thread is attached at this point P. So A will go in a path like this. So once we release B, A will go in a path like this and it's going to hit the wall at some point over here. So we have to calculate the speed of A and B, VA and VB, the instantaneous speed of A and B when A is just about to hit the wall. So at the instant when A is about to hit the wall, this wall over here. So just start working on the geometry aspect of it, how the motion of A will look like, how the motion of B will look like. Imagine that B hasn't hit the pulley yet. B is not yet hit the pulley. Or you can even imagine that this thread is a bit longer. So B is not yet hit the pulley. Or B is in no danger of hitting the pulley before A hits the wall. But B is of mass m and A is of mass 2m. First of all, think what type of path will A move in? Think of work energy theorem. In fact, conservation of mechanical energy for the system that consists of A plus B plus the thread plus gravity. Okay, and the moment you think about this, you will also have to think about constraint relation. PAVB. That you get by virtual power. And you'll also have to think of the vertical displacement for B by geometry. So I've given you lots of hints of what all you have to do here. So we'll discuss very shortly, but try this out yourself first. A and B have mass 2m and m beta. I use the masses are 2m and m. Okay. So when you write the equations, that factor of m will cancel out. So you will get your answer in terms of L and G. In fact, if you want a numerical answer in meter per second, then only the value of L and G is required. But here you can give the answer in L instead of a numerical value. And I used to answer your last question. We can calculate the ratio of VA and BB in the previous question without virtual power, but it will involve calculus. It will involve conserving the thread length and differentiating a term and calculus and all that. So it will be a little bit lengthy. Okay, when we finish this question, I'll explain that also. Okay, so let's figure out some things here. So first of all, we'll see that the path of the block A will be a circular motion about the point P because the thread is of fixed length. So that thread joining P with the point A, that will remain taut. And just before A is about to hit this, it will go in circular path, make a downward displacement of L, and is about to hit the wall with a horizontal velocity because it's tangential to the circle. So its instantaneous velocity will be like this, because by then the thread would just about have become like this. The thread joining A with the wall just about have become vertical. It's of length L, this thread. And the other thread, which is joining A with the block B through the pulley, that would be now in this kind of position. This would have some upward velocity VB. Okay. So if these were the positions at t equal to 0, now at this particular instant of time, when this is about to hit the wall, this is going to be the position. Okay. So now this thing has to be determined. So first of all, if this has gone up through a distance y, you can see this thread length here, let's say this total thread length is going to be how much? Let's say it's z. It is square root of L square plus 2L square. So it is L root 5. Okay. So obviously this angle is 90 here. So y, just a second, I'll share that file again. Yeah. So यहाँ से how much thread is getting pulled? Initially, this was L na, from here to here. From the pulley to where A is joined with this thread, the length was L, and now it's got pulled to how much? Root 5L. So this displacement y is going to be z minus L. So that is root 5 L minus L. So that is the first thing. Okay. Secondly, you can see that if this angle here is theta, that's the same thing as this angle theta. So you can see the virtual power concept now, that minus VA T cos theta plus TVB should be 0. So VB should equal to VA cos theta. And from that triangle, you can see that cos theta's value is 2 by root 5. That's a second. Okay. And then our work energy or conservation of mechanical energy for A plus B plus the thread plus gravity. So change in kinetic energy of A plus change in kinetic energy of B plus change in gravitational potential energy of A plus change in gravitational potential energy of B should be 0. So half 2m VA square plus half m VB square minus 2m GL, because A is coming down by L, plus m GY is equal to 0. This is the last equation. So now in this equation, we will substitute VB as 2 by root 5 VA. Okay. And we will substitute Y as this. So this equation will become half of 2m VA square plus half m 2 by root 5 VA square minus 2 mgl plus mg into root 5 minus 1 L is equal to 0. So we can take VA square common 1 plus ये कितना हो जाएगा 2 by 5 is equal to GL 2 minus this, so 2 plus 1 minus root 5. So you can see we'll get something like this. 7 by 5 VA square is equal to 3 plus root 5 GA. So our VA will come out to be square root of 5 by 7, 3 plus root 5, sorry, 3 minus root 5, my mistake. This one. So this is in fact a question IIT-JEE subjective paper a few years back. So this is an actual JEE question. I don't exactly remember which year, but if I'm not mistaken, it is either sometime in the late 90s or around 2002 or 2003, something like that. Quite a few years back, 2 decades back. How did we find y na? Amog, see what is happening. ये जो thread है ना, which is joining A and B, इसका length यहाँ पे क्या है? Suppose it is L plus some H. So that L plus H has to remain conserved now. And the second diagram, you can see it's root 5L plus this section now, which has become H minus Y. So you can see that Y is equal to this. Is it clear, Mo? Okay. So, you know, that's the thing. In both these questions you saw, we have to use thread length conservation to find displacement. And then we have to separately use virtual power to find the constraint relation between VA and VB. Okay, just finish writing this down. Let me know if there's any doubt with it. Make sure you're clear with both the constraint relations. Yeah, so Amarup, why did we consider gravity in the systems, Nikita? Because then otherwise, no, if we don't consider gravity within our system, then the force of gravity will become an external force for us. Na? Then we'll have to write our work energy theorem like this, that work done by gravity on A plus work done by gravity on B is equal to change in kinetic energy of A plus B. So you can do that also, but since you already know a formula, na, direct formula for gravitational potential energy. So we have to take gravity within our system so that we can take the gravitational force as internal conservative force. Okay. Yeah, Vaishnavi, you want to see the question again or the solution? Okay, I'll take you through the solution again. And Somarup, the constraint relation I'll explain again. So there are two constraint relations here. The second one, the virtual power one. So virtual power one में देखो क्या हो रहा है? At the instant when B is going to hit the wall, B's velocity is in this direction. Okay. Whereas the tension acting on it is in which direction? It's along the thread. So this angle is theta, no? So the angle between tension and velocity, it is basically what? It's 180 minus theta, no? So the power developed by tension on B is actually TVB cos 180 minus theta. So it's minus TVB cos theta. And at that same instant on the other side, sorry, this is A, my mistake. This is the block A. So this is the block A. It's about to hit the wall with a speed VA. So power delivered by tension on the block A, that will become TVA cos 180 minus theta. Okay. So that's why here, as you can see, it becomes minus TVA cos theta. Whereas on the other side, on the block B, the tension is acting vertically upwards and the velocity is also vertically upwards. So the power delivered by tension on the block B is plus TVB. So that's this term here. And their sum should be 0 because net power. Is it clear, Somaru? Okay, good. Vaishnavi, the solution is clear now fully? Okay, very good. Okay, now for a moment, we'll just go back to Amog, your question about the previous one. How can we find the constraint relation without using virtual power? So if we are not using virtual power now in this one, we have to find the constraint relation like this, that at any arbitrary instant, okay, when this angle is some theta, okay, so what we'll do is we'll take this part of the thread as Z and this as Y. So the total thread length is what? It is Z plus 2Y. So that is the total thread length which is constant. Okay. So dz by dt plus 2 times dy by dt should be 0. Okay. Now you see here that if we take this as h and this as x, so we can write z as root of h square plus x square. Okay. And if this is having an instantaneous velocity va like this, so va is actually minus dx by dt. Okay. And similarly here b is moving up. Okay. Sorry, b is moving down, my mistake. Okay. So on this side you can see this is plus dy by dt. Okay. So this and this will now have to be plugged into this equation. So this equation becomes differentiation of root of x square plus h square. So it becomes lengthy, okay, plus 2 times dy by dt is equal to 0. Now you'll have to use the chain rule here for this differentiation. So this will become 1 by 2 into x square plus h square to the power half minus 1 into differentiation of x square plus h square, which is 2x because h is a constant, into dx by dt plus 2 times dy by dt is 0. So this whole term will give us x dx by dt divided by square root of x square plus h square plus 2 dy by dt is equal to 0. Now you plug in these two things here. So dx by dt can be substituted as minus va. So x into minus va upon root of h square plus x square plus 2 times vb is 0. In the diagram you can see that h upon root of h square plus x square is nothing but x by z. So x by z va is equal to 2 vb, and x by z va is nothing but cos theta. So va cos theta is equal to 2v. So this is how we would manually calculate the constraint relation by using trigonometry or by using basic geometry. I mean, not even trigonometry, geometry and differentiation. Thread length, basically thread length conservation. Whereas the virtual power method is the shortcut of doing this by just directly equating the power delivered by tension to be 0. Okay, Aman, hope it is clear. Okay, so in general, this type of calculation is avoidable. No, you don't want to get into so much calculation. What you want to do is use the virtual power method wherever possible. Okay, so Aman, I'm hoping this is clear for you. Okay, so these are some of the applications of work energy theorem. Now moving on to, or rather moving back to, a little bit more analysis about the relationship between internal conservative force and potential energy. Okay, now this is very important. So what we had seen earlier was, by definition, the change in potential energy of a system is negative of work done by internal conservative force. Or we can say that delta U is in general minus of path integration of the internal conservative force from initial to final. Okay. And using this formula only, we saw in general, we saw the specific example that change in potential energy of the spring was half k into x final square minus x initial square, and change in potential energy was mg delta y. Okay. So these were specific cases of it. Okay. Now let's discuss a little bit more about this. So we can also say that during a small displacement ds, okay, so here du is the change in potential energy during a small displacement ds. Okay. So now we can also see, for a one-dimensional system, okay, along the x-axis, potential energy will be a function of x. Okay, because in general, what is potential energy? Potential energy is a function of position. It is a function of position, or what we call configuration. So for a system, the configuration has to do with the XYZ coordinates. No? So in general, it is a function of XYZ. Okay. So for a 1D system, it becomes a function of just the one coordinate, because the Y and Z coordinate are not changing. It's one dimensional. Okay. And the internal conservative force also will just have one component. Fy and Fz will be 0 for the internal conservative force. So only one component will be there. And also this, because the motion is one dimensional. So dy and dz are 0. So this above equation here, this reduces to, when we say du is minus of f internal conservative dot ds, this now for a one dimensional system reduces to minus f dx for a 1D system, where f is the x component of the internal conservative force. Okay. So now the reverse of this relation is that f is minus du by dx. So this becomes the all important equation for us. So for the 1D system, u is a function of x. Okay. And the x component of the internal conservative force, how we get that? By differentiating with respect to this. Okay. So make a note of this first, then we'll discuss more about its applications. So if we know potential energy as a function of x, we can calculate the internal conservative force by using this formula. Okay. So before you note this down, you can also in fact look at an example. Potential energy of a spring is half kx square. So the spring force should be minus du by dx. So that is minus d by dx of half kx square. So that means the spring force has the x component of minus kx. That means the spring force as a vector we'll write as minus kx I cap, which is correct. When x is positive, the direction of the spring force is along minus x. When x is negative, the direction of the spring force is along positive x. This is not the magnitude of the force here. Okay, here it is the x component of force. Okay. So it can have both positive and negative sign. Do not think that why we have written the magnitude of a force with a negative sign, because you're talking about a force in a 1D system, the force vector in a 1D system. So that can have a negative sign because the direction of the component can be along positive or negative direction. So anyhow, so in a 1D system, the relationship between potential energy and force, the internal conservative force, is given by this formula, that internal conservative force is negative of differentiation of potential energy with respect to position. Yes, Nikita, I'll explain the example again. Just note down up to this f equal to minus du by dx. I'll explain again. Okay. So see, now suppose we are in mass system like this. Okay, where we are now taking this as our x-axis. This point is our origin. So we know that here the spring is at natural length. The potential energy of the spring is 0 at x equal to 0. But we also know that when we stretch the spring, to this position, the potential energy is half kx square. Or when we compress the spring, okay, to x equal to minus x, again the potential energy is half kx square. Okay, so we know the formula. So given that the potential energy of the system is known to us, half kx square, now we have to calculate the spring force, that is the internal conservative force. Okay, so we go to the definition. The definition is what? That delta U is minus F dx integrated. Okay, so in other words, du is minus F dx in a 1D system. So what about F? It becomes minus du by dx. Where what is F? Where F the internal conservative force in 1D form. In 1D form, we don't write the unit vector. We just write it as with a sign plus or minus. Is it clear now, Snikita? So how we'll find this now? We'll use this formula. So the spring force should be minus du by dx. So minus of derivative with respect to x of this potential energy. So k is a constant. Okay. Now the minus sign will just show us the direction of the force. So after differentiation, you'll see that this becomes minus half k into differentiation of x square. No? So the spring force becomes minus kx. So what the minus sign is showing us that the spring force always points to x equal to 0. So when x is equal to plus x, the spring force will be minus kx I cap. When x is equal to minus x at a compression, the spring force will be minus of k into minus x. So it will be plus kx. So at a position of negative x, the spring force is plus kx I cap. At a position of plus x, the spring force is minus kx. So that is the information we are getting from this. Okay, good. Okay. So this is like an example. Of course, we'll look at more complex examples also next. But okay. So the important thing for us to remember is that in any one-dimensional system, suppose it's along the x-axis, the potential energy will be a function of x, and the internal conservative force will have only an x component. So that internal conservative force's x component is given by this relation. Okay. So this is in fact given a special name. Okay. This is called, this side, it is called negative gradient of potential energy with respect to x, or we'll say it is in general negative gradient of potential energy with respect to position. So the word definition of this becomes like this, that the internal conservative force equals to the negative gradient of potential energy with respect to position. So here we are using the term gradient. So the term gradient, okay, in one-dimensional form it is given by this term. In 1D form, the gradient is given by this operation. It is basically rate of change with respect to position. So it's a special name given to that operator. It's called gradient. Whereas when we say rate of change alone, it means rate of change with respect to time. So we say velocity is rate of change of displacement with respect to time. So it is differentiation with respect to time. But we say potential energy, or rather force, is negative gradient of potential energy, because it is differentiation, but not with respect to time, with respect to position. So when we are calculating the instantaneous gradient or the instantaneous rate of change with respect to position, that term is called gradient. You can just additionally note down this point over here. This will become more significant as we go along. So you should know this like a, like a conceptual idea, that internal conservative force is what? It is negative gradient of potential energy. I'm using the term gradient, I know I'm talking about rate of change or differentiation with respect to x or y or z, whatever the coordinate be, or whatever the position is given by. The example, okay, yeah, so the example is of spring force. So given the spring's potential energy is this, now how we'll calculate the spring force? So for that we'll use this definition here, that force is negative gradient of potential energy. The internal conservative force is negative gradient of potential energy. Okay, Aman, this is clear. Sorry, Amok, this is clear. Yeah. Okay, good. Okay, now let's take a more general example. So suppose we have something where a particle moves, let's say, along the y-axis, okay, under the action of only conservative force. So that means the external force on it is zero. The non-conservative force on it is zero. Okay. Such that its potential energy is given by the formula U is equal to, let's say, um, 20 by y minus 10 by y square, or yeah, something like this. The potential energy is given by this kind of formula, where U is in joules and y is its y coordinate in meters. Okay. So first of all, find the formula for the net force acting on the particle as a function of y. And secondly, if its mass is equal to 2 kg, find its acceleration at the y coordinate equal to 1 meter. When it's at the y coordinate equal to 1 meter, how much is the acceleration? In fact, let's do two parts. Okay, so this is not your everyday mechanical system with spring and gravity and all that. This is a theoretical situation, or what we can say is a hypothetical situation, that some kind of imaginary force which is conservative is acting on a body, making it move only along the y-axis, or on a particle making it move only along the y-axis, such that now the potential energy of it is given by this. So from this, what we can say about the force? Okay, so here we'll use this relation, that here it's a 1D system along the y-axis, and only conservative force acting on it. So that means the internal conservative force for the system we can take as F j cap, such that F is minus du by dy. And because there is no external and non-conservative force, the net force acting on the body is nothing but the internal conservative force. Yes, that's correct. Okay. So now this internal conservative force will calculate by negative of gradient with respect to y of that formula, which was 10 by y, sorry, 20 by y minus 10 by y square. So just use this. So minus of 20 into differentiation of y to the power minus 1. Okay, and this will become minus minus plus of 10 into differentiation with respect to y of y to the power minus 2. So as you can see, this will become 20 into minus 1 by y square plus 10 into minus 2 by y cube. So it will become 20 1 by y square minus 1 by y cube. It's a very interesting type of force which we are getting, which is like this. Okay. So the net force acting on that body we can say is like this. So it is in fact undefined at y equal to 0. Okay, you can see that this force cannot be defined at the coordinate y equal to 0, and this force itself is 0 at y equal to 1, which also goes to show us that y equal to 1 will be an equilibrium position, because the net force will be 0 at y equal to 1. Whereas at y equal to 2, for example, you can see that the force will be along the positive y direction. Whereas at y equal to something like 0.5 or 0.8 or less than 1, the direction of the force will be along the negative y-axis. Okay. So the second and third part we'll calculate by now using this formula of force that we have got, which is the third part. Which is the first part. So for the acceleration, we'll find the force divided by the mass, which is given to us as 2 kilograms. The main thing was finding the formula of force. Now you have to just substitute the y coordinate and then use equal to ma to find out the acceleration. So let's add just one more part to this. At y equal to 0.5 meters, so you see that it will have a negative acceleration. I mean, along the negative y-axis, the acceleration will be, whereas at y equal to plus 2, it will be along the positive y direction, the acceleration. Okay, so now you can see that at y equal to 1 meter, the net force on it is 0. So the acceleration will be 0. At y equal to 2 meters, you can see the net force acting on it. Just have to use this formula. So this will become how much? 20 upon 2 cube. So that's 20 by 8. So that is 2.5 j cap. So the acceleration will become 1.25 j cap in meters per second square. Or you can say the acceleration is plus 1.25 along y-axis. Okay. Whereas at y equal to 0.5 meters, interestingly, the net force will become, this will become 20 into minus 0.5 divided by 1 by 2 cube. So this will become 8 into 10, but with a minus sign. So minus 80 j cap. So the acceleration will become minus 40 j cap in meters per second square. Or you can say the acceleration is minus 40. The y component of acceleration is minus 40. Or you can say that acceleration is minus 40, sorry, is 40, but along the negative y direction. The magnitude of the acceleration is 40 meters per second square, but it is along negative y-axis. Okay, so hope this is clear. I mean, this is just calculation. Okay, the main thing is the formula minus du by dx, or negative gradient with respect to, I mean, negative gradient. Gradient itself means rate of change with respect to position. So that was the important aspect. Okay, now we will see something interesting related to this. Because the internal force is negative gradient of potential energy in general, the internal conservative force equals to negative gradient of potential energy. So basically this means, this implies that the direction of the internal conservative force always points towards a state such that potential energy should decrease. So I'll explain to this point with a couple of graphs and things also. So the direction of the internal conservative force in a system always points in such a way that it tries to take the system to a configuration or to a state where the potential energy will tend to decrease. So what this tells is that the decreasing potential energy implies more stability for a system. The system tends to stabilize in that direction in which the potential energy decreases. Now we can think of this with a logical example. Okay. A spring will decrease in potential energy because this potential energy is given by the formula half kx square when it relaxes back towards natural length. Okay, it will decrease in potential energy. No? So if initial x is plus x naught, but final x is 0, the change in potential energy of the spring will be minus half kx naught square. So it's decreasing in potential energy as it's relaxing. If initial x is minus x naught, it's compressed, but final is back to natural position, then again your change in potential energy of the spring is minus half kx naught square. So every time the spring goes from a state of stress or a state of deformity to natural length, it is stabilizing. So what is happening as the spring goes from a deformed state that is x equal to plus or minus of x to natural length or relaxed state x equal to 0, okay, it stabilizes. So its potential energy decreases. So this thing holds true for not only the spring system but any system in general. For any system, if your potential energy is decreasing in a certain direction, then the system is stabilizing in that direction. Or in other words, the internal force will always try to move the system. It will always point in the direction in which the system's stability is increasing, or in other words, its potential energy is decreasing. Okay, so internal conservative force in any system always points in the direction towards lower potential energy, lower amount of potential energy, therefore more stability. So I've given you the example of the formula of the spring's potential energy to explain, but we will also understand this from a general graph. But make a note of this point first. So relationship between potential energy and force, internal conservative force, is not important only from the point of view of calculations and finding out formula, etc. It's also important from the point of view of trying to understand the behavior of a system. A system on its own, in the absence of external forces, the internal forces of the system will always try to make it move in the direction in which its stability increases. So in terms of potential energy, the system will always try to lower its potential energy. The internal forces in the system will always try to make it move in such a way that it lowers its stability. It lowers its potential energy, and thereby it gains stability. Yeah. Okay. So let's also understand this from a point of view like this, that suppose we are looking at the potential energy versus the x coordinate as a graph in some kind of a 1D system. So this is the graph of potential energy as a function of x for a 1D system. Along the x-axis, needless to say. Now we can see something very interesting here. So first of all, let me draw the graph. So supposing it's some kind of imaginary function which has this kind of a behavior. So you can see that, let's say this coordinate is A, this coordinate is B, then this coordinate is C, and this coordinate is D. So the domain of the function that I've taken is A to D. So you can see that the potential energy as a function of x for x equal to A to D. Okay. Now it behaves such that the potential energy is increasing from x equal to A to B. Okay. Then potential energy has a local maxima at x equal to B. Okay. Then again it is decreasing to C where it has a local minima. Then potential energy is decreasing x equal to B to C where it has a local minima at x equal to C. And then again potential energy increases from x equal to C to D. So this is the entire behavior in the domain. This is the behavior. So now if you see what can we say about force? So the internal conservative force F in this system, it will be minus of du by dx. So in terms of graph, F is negative of the slope of u versus x at any point. Okay, so therefore you can see that F is negative from A to B. Okay, because the slope is positive, then F becomes 0 at x equal to B because there is a local maxima. So the slope becomes 0. Okay, then F again becomes positive because the slope is negative from B to C. Then again at the local minima point, the instantaneous force is 0, and again force is negative from C to D. Okay. So this will tell us something very interesting about the local maxima and the local minima points. Okay. They are points where force is 0. So they are equilibrium points. This point and this point, they are equilibrium points. But if we look in the neighborhood of those points, the force on either side of them will tell us something very interesting. It will tell us whether it is what we call a stable equilibrium or an unstable equilibrium. So I'm coming to that. Just make a note of this first. Okay. So again, this is some hypothetical graph. Okay, this is some imaginary graph of potential energy as a function of the one-dimensional coordinate. Suppose it happens to be like this. Then what we can say about the force in the system? We can understand the direction of force by using this relationship that it is negative of the slope. All right, so hope this point is clear. Now, see, let's try to analyze this information about force now, also in a sort of graph, but without making a real graph, we'll think of it more like a number line along the x-axis. So we have a sort of just an x-axis, and we are trying to analyze the force just in terms of the force at different points. See the conclusion that we'll come to. This is the x-axis. So this was our starting point A, this was the point B, this was the point C, this was the point D. So what was happening is, as long as we are just talking about the direction of the force, you can see that between A and B, the direction of force is negative. It's a negative direction force. Okay. At B, the force is 0. Okay, at the point B. Then again, between B and C, what is happening? The force is positive, so it's pointing in this direction. And then between C and D, the force is again negative. It's pointing in this direction. Okay. And at C, the force is 0. So this tells me that if I put the particle at the point x equal to B, what will happen? It will be in what we call an unstable equilibrium. Unstable equilibrium का मतलब क्या है? That when you put the particle at B, the force on it is 0. But if you displace it on either side of B, it will run away because the force is pointing away from equilibrium. You can see in the above graph that when you take the force will push it away. When you take it to this side, the force will push it away. Whereas if you see the point x equal to C, now that is a very interesting point. It's a stable equilibrium point. At the point C, what is happening? But if you take it to this side of C, or you take it to this side of C, the internal force is pushing it back towards C. So this type of force is called restorative force. It restores it back to C. Restorative force towards the point C, or x equal to C. That is why x equal to C is a what we call a stable equilibrium position. It tend to be stable at that equilibrium position, because even if you try to push it a little away from equilibrium, the internal force will take it back. Whereas this point, the point x equal to B, is such a point that at that point the force is 0. But even if you move it slightly away from it, the body will tend to run away from that point. So it is an unstable equilibrium point, because these forces are non-restorative. They don't restore it back to equilibrium. They are non-restorative force with respect to x equal to B. It is taking it away from x equal to B. Whereas on either side of C, you can see the force is restorative. Okay. So we will write about this in detail also in a note, but first you just understand the correlation between this information that we had, that where the force is positive, where the force is negative, and this number line kind of graph. I'm just showing in which region the force is pointing backwards, in which region the force is pointing forwards, and which are the points where the force is 0. So that is telling me something important about the point x equal to B and the point x equal to A. So all that is coming initially from where? The graph of potential energy versus x, which we had started with. By looking at the slope of that graph, we understood that where the force is positive, where the force is negative, and where the force is 0. And now by looking at that, we can see that the point x equal to B is becoming an unstable equilibrium point, whereas the point x equal to C is becoming a stable equilibrium point. And it's no wonder, because this is a local minima. So we said the lower the potential energy, the more the stability. Whereas there's a local maxima. So higher potential energy means unstable. Lower potential energy in that neighborhood or local minima means stability. So that's another way to remember that always at a minima point, we will get the stable equilibrium. Whereas always at the maxima point, we will get the unstable equilibrium. Okay, so this analysis is very important. We'll discuss, just write this down first. Okay, so let's understand this in words now. At the point of local maxima, the above example x equal to b, for potential energy as a function of x. Okay, force is 0 at x equal to b, but force is negative to, or you can say negative at x equal to b minus delta x, and force is equal to positive at x equal to b plus delta x. Okay. So that means force is 0 at b. That means there's an equilibrium point. Okay. But on either side of the equilibrium point, you can see that if this is your x equal to b, now at this point the force is like this, and at this point the force is like this. So these are non-restorative forces. Okay. So what this implies finally is that x equal to b, which is the local maxima of potential energy, is a point of what is called unstable equilibrium. That is the definition of unstable equilibrium now. Okay. That it is a point at which the force is 0, but on either side of that point, or when we displace the body from that point, there is non-restorative force taking it away from equilibrium. So it is unstable in nature. So another way to define it is that any unstable equilibrium point becomes the local maxima of potential energy function. Okay. Whereas at the point of local minima, like in the above diagram, x equal to c, for potential energy as a function of x, what happens? Force is 0 at x equal to c, but as you can see, force is positive at x equal to delta x, and force is negative at x equal to c plus delta x. So at the point x equal to c, force is 0, but before it, at a point like this, the force is positive. After it, at a point like this, the force is this. Whereas at this point, the force is 0. So that means there is equilibrium, okay, but there is also restorative force. Okay, so that means x equal to c, which is the local minima of the potential energy function, is a stable equilibrium position. Okay. So this is the understanding of stable and unstable equilibrium, which is a very important part of the understanding of potential energy itself. So physical examples of this. Okay, are like this. Suppose we have a situation where obviously spring mass system is the easiest example. X equal to 0 is the stable equilibrium position, because you can see the graph of potential energy versus X will have this kind of a relation. So at X equal to 0, there is local minima. Okay. But another example could be that suppose we consider a system where we have a smooth slope like this. Now this is not exactly a 1D system, but anyhow we'll understand. The potential energy is a 1D function. So this is a smooth slope. Okay. So you can see that at this position, force is 0. Okay. Net force will be 0. Okay. But if you take a body to this position, the force is acting like this. It is non-restorative. If you take a body to this position, you can see it is again non-restorative. So this position A is the unstable equilibrium position. Okay. And for the given system, that will also be the point where it is the maxima of gravitational potential energy, because the y coordinate, the vertical coordinate, is maximum. So this is the most natural example of a unstable equilibrium position. Whereas if you have this situation, then this point here becomes a stable equilibrium point. Another example could be like this, that you have a system where we have two fixed charge particles, and now on a movable block we have some positive charge. Okay. So this is slidable, whereas these are fixed. Okay, so this position will be equilibrium. Okay, but you will see that if I move this from this equilibrium position to this side, for example, okay, and I'm calling this A and this B, now the repulsion due to B will become more than the repulsion due to A. So what will be the direction of the net force? It will be like this, because it has come closer to B. So B's repulsion dominates on this side, whereas if you take it to the other side, A's repulsion will dominate. So this is which type of equilibrium point now? There is restorative force. So this point becomes stable equilibrium. Whereas same system, suppose I take the particle on the block as a negatively charged particle, it is minus q, and these two are plus q. Now you will see that the same thing will become an unstable equilibrium, because the attractive force of one will dominate over the attractive force of the other when you bring it near. So here net force is 0. But now when I bring it to either side, for example, if I bring it to this side, this attractive force of A will dominate over the attractive force of B from the other side. So अभी इस पे क्या होगा? The net force will be pointing in this direction, away from equilibrium. So you can see that this is non-restorative. So just changing the sign of the charge on the middle one from plus to minus will make this an unstable equilibrium point. No, Jewel, why we can't say the spring is in equilibrium position? Because the net force will not be 0, no? Unless there is some other spring force also, and the net spring force is becoming 0. You understanding the point? Okay. So supposing we have done something like this, that or you can take a system like this where a block is hanging vertically, okay, in equilibrium. So right now the spring force is balancing mg. Okay, now you can see that this is an equilibrium position. Now if you take the total potential energy as the spring's potential energy plus gravitational potential energy, okay, then you will see that when you take it above from here, your potential energy will definitely decrease. Will definitely increase, because now it will have a downward acceleration, because mg will become greater than kx, because x has become less than x naught. Whereas compared to this, if you take it at a lower position, so here it has become, let's say, L plus x prime. Now x prime is greater than x naught. So here what will happen? It will happen because now kx prime will dominate over mg. So spring force will dominate. So you can see that this is now a stable equilibrium position. So this is an example of a system where the spring is stretched in stable equilibrium position, because there is some other force also. There's mg also. Okay, so we'll discuss more about applications of stable equilibrium and unstable equilibrium position in the next lecture. Okay. Now, what I want to do is just take 5 minutes to quickly run through the questions from work energy and Newton's laws from the test which has just happened. Just give me a moment, and if required, I will give you some hints in some of the questions, so you can try them again. And on Sunday's class, which we have as an extra class this week, we can discuss about it. Okay, so just give me a moment. So today let us just take a look at the advanced paper. Yeah, I'm sharing the questions. Tell me if you need to understand any of these. So first question, does anybody have a difficulty or doubt in the first question? So here you have to understand that this is moving with uniform velocity. So it is an inertial frame. Okay. So the free body diagram will only have static friction balancing mg sine theta, mg, and normal reaction. Now what is happening? The whole lift is moving upwards with velocity v. So after some time, when the lift has made a displacement of Vt, so the block has also made a displacement inside the lift of Vt. So displacement will be Vt upwards. Okay. So you'll have to calculate work done by friction by calculating the dot product of static friction with that displacement. So this is the hint I'm giving you for the first question, in case you have a doubt in it. This should be fairly easy. Now this question, the third one, I'll give you a hint. So see, in this question, what is happening is this is fixed, because there's a wall over here. So that means the block B's motion will be along this inclined plane, which is at an angle alpha. So B's own velocity now, it will be along this direction. BB will be along this direction, which is parallel to this. Okay. Whereas the normal contact force that is acting on B will be along this sort of direction. Okay. So you have to calculate the dot product for power. Okay. Whereas the block A, how A will be moving. Now the block A you can see will be moving horizontally. Okay. So on the block A, the normal reaction is acting like this. Okay. And his own velocity is in this direction. Okay. So n dot VA, it will give you some positive quantity. Okay. And here n dot VB will give you some negative quantity, and the two should balance each other because net power should be zero. Okay. And just remember that these angles are not the same. On this side, this angle is theta, and on this side, this angle is alpha. So a bit of complication will come in the calculation of the virtual power thing. So make sure you're clear with all the angles and dot product over here. Okay. This VB is parallel to this, so it is like this. From the vertical, we'll be making this angle alpha, whereas this N is along this normal. So this will be making an angle theta like this with the vertical. This. So it's a bit complex, the angle between these two. Okay, next up, this should also be pretty easy. Okay, now in this you can see, you can do a bit of like guesswork in this type of problem. Okay, what is happening? You're finding potential energy. Okay, now potential energy is given by this function. Okay, and initially it is located at the origin. So you can see initial potential energy is zero because x coordinate is zero, y coordinate is zero. Okay. Now, if it is moving with a velocity like this, okay, then you can find the initial kinetic energy. Okay. Single choice is given. No, this is more than one option correct. This is more than one option correct question. So this would be in the section Ayush, section 2 में था ये. Okay, I'll check it out then why this was in the. Okay. So anyway, so here you have to understand that if the potential energy is given by this formula now, you have to understand that the internal conservative force, it is constant, because minus of work done by internal conservative force, which is delta U, okay, it is like this, it is minus 7x plus 24y. So that means because it's linearly proportional to x and y, okay, so that means basically your internal conservative force is 7i cap minus 24j cap. This type of force will give you this type of potential energy. Because if you take displacement as xi cap plus yj cap, so now you can see that negative of work done is your change in potential energy. So that will give you that minus 7x plus 24y. So basically from this expression, you have to understand that your internal force is like this, 7i cap minus 24j cap. So from this, you will now get the acceleration. The mass of the body is 5 kg. So your acceleration will become 7 by 5 I cap minus 24 by 5 j cap in meters per second square. So your acceleration is known. Okay, so from that you can find after 10 seconds, after 4 seconds, what the position will be and all that. Or you can find the magnitude of acceleration from this. Okay. So from here onwards, it's kinematics. So just try it out with this hint, okay, and I'll see what happened in the paper. It was supposed to be in the multiple choice section, not the single option section. This is fairly easy. I think you should be able to understand this question. Okay. Now let's come to the paragraph question. So here you can see that the force is like this. Now the force is a variable force which has a constant x component. Now you can also see that path one is actually the straight line y is equal to x. So at any point in this straight line, what is happening? The force, which is 20 I cap plus 2x j cap, what kind of work it will be doing? The displacement is dx I cap plus dy j cap. So f dot ds is going to be 20 dx plus 2x dy. But now we can use this relation that y is equal to x on this straight line because it's passing through this point 5, 5. So the equation of this straight line is y is equal to x. So here I can replace x with y. So this becomes 20 dx plus 2y dy. And now you can integrate this. So when you integrate this from here to here, you will get the as 20 into 5 plus y square. So that is 5 square. So 125 joules will be the work done in the first path. Okay, we'll pick this up in the next lecture. Then you have a KVPY class also coming up. Okay. So for path 1, I hope all of you understood the method to calculate work done. For path 2, you can just refer to this type of question that we have done earlier. Okay. You can see that here in this part, the work done will just be 20 I cap dot product with, because the y component will not matter, 5 I cap. Whereas in this part, the x coordinate is fixed. Okay. So the y component of force is becoming fixed. It is becoming 10 j cap. Okay. So the work done will again be Fy into delta y because you're moving along the y-axis. So it's very easy to calculate the work done. So ultimately you will see that the two paths will give you two different work done. So therefore the force will come out to be non-conservative. Okay. So just try out these questions if you haven't done them before, and the remaining questions we'll discuss in the next lecture on Sunday. So that's it for today's session, people. Please make sure that you go through the equilibrium positions concept very carefully once. Okay. And send me any other doubts that you have from the test. We'll discuss the remaining questions on Sunday's lecture. Yeah, Merry Christmas to all of you also. Okay. Yeah, Ayush, you can send me the doubts on WhatsApp, or we will discuss on Sunday's lecture. So wishing you all a very Merry Christmas, and